So let's talk now about simulation of a Gaussian random vector. We know how, once we know that, we can simulate mixture Gaussians, right? We've already talked about that. So let's start with this, what about a Gaussian random variable? So it's a scalar Gaussian. Well, what does standard software give you? Standard software gives you Gaussian 0, 1, so-called standard normal or standard Gaussian random variables. That's available from a simulator. So if I want to generate an X which is Gaussian with mean m and variance sigma squared, but I'm given a Z with Gaussian with mean 0 and variance 1, how do I go from Z to X? Right? And the answer is simple. Basically, if I scale Z by sigma, the variance will scale by sigma squared, and so Gaussian 0 sigma squared random variable. And if I want a non-trivial mean, then I just add the mean to that, right? So m plus sigma Z is Gaussian m sigma squared, and that's the desired distribution of X. And now we have to talk about how we generalize this to higher dimensions. So when simulating Gaussian random vectors, what we're going to use is the following fact. First is if, let me get the pen, if a vector U is Gaussian, it's a Gaussian random vector, then any affine transformation, affine is just a term we use for linear plus constant, is also Gaussian. So basically A U plus B, where A is any constant matrix and B is any constant vector, is Gaussian, right? That's what we are saying. So basically that means if I take a bunch of Gaussian random variables that the jointly Gaussian random variables that standard software has generated for me, I can get other Gaussian random vectors from them. So that's one thing. Now, of course, but I want something with a given mean and covariance. So let's look at how means and covariances evolve under affine transformations. So this is general. This doesn't need to be just for Gaussian random variables. But if U has mean m sub u and covariance c sub u, then AU plus B, the mean of that, is just A times the mean of U, it's just linearity of expectation, and B, constants just pull out, right? So so the mean just sort of propagates in that fashion. And the covariance of AU plus B, so the covariance of it with itself, is, remember that the covariance, you subtract out the mean before computing covariance. So this constant should not matter. And it's pretty easy to see that you have these two terms that interact with each other. And the answer is going to be, the covariance of AU plus B will be A times CU times A transpose. So that's what the covariance is going to be. So now, if we are going to use those two things plus the standard Gaussian random variables that we know how to generate in any software, and generate arbitrary Gaussians from it. So what are we given? We are given independent Gaussian 0, 1 random variables from the simulator. We collect them into a random vector of the right dimension. So that random vector will also be a Gaussian random vector. That's easy to check. Its mean vector will be 0. And remember that the independent random variables are also uncorrelated. The covariances are 0. So basically, the covariance matrix for this will be the identity. So now, if I want to, generate a desired mean and covariance from this, so basically what we want is X having mean vector M and covariance matrix C. If we can find some matrix A such that the covariance matrix is A times A transpose, then A times Z is Gaussian with mean 0 still, right? And covariance AA transpose, which is equal to C. So that's great. That's just like what we did for the scalar case, where we multiplied by the standard deviation and we got the right variance at the end of the day. And then when we want to add a mean vector to it, I just add it like that. So mean plus MV is NM. The mean does not change the covariance, and MC, right? So that's how we generate stuff. Basically, we somehow factor the covariance matrix like so. Basically, I have this C equals AA transpose type factorization. And once you have that, you can basically just use these IID Gaussian random variables that the software is spitting out for you and create the desired distribution from it. So now how do we find an A such that this C equals AA transpose is satisfied? Well, there are many possible choices. So one choice is to use this so-called spectral factorization of the covariance matrix. What does that mean? It means that for a covariance matrix is always non-negative definite, which means it has positive eigenvalues, and I can always write it in this fashion. Suppose I have these lambda j's are the eigenvalues and u sub j are the corresponding eigenvectors. Then I can write the covariance matrix like so, and it basically works as follows. These are UJs are basically the axes of the ellipses that form the that provide these equiparable contours for the Gaussian distribution. So UJs are pointing towards this axis, and lambda j's are how big those axes are, or rather square root lambda j is how big those axes are. So that's what it looks like. And basically, I'm operating independently across these axes. So I can now actually, when I take, say, if I want to take, say, the square root of the covariance, that pretty much boils down to, not exactly boils down to, taking the square root of the eigenvalues and then just having them the UJ transpose terms as before. Now UJs form an orthonormal basis, and I can also write these things in matrix forms as U lambda U transpose for the covariance matrix and U lambda to the half U transpose for the square root of the covariance matrix. So what is U? U has U1 through UD as the columns. So the columns are the orthonormal eigenvectors. And since they are orthonormal, when I take U transpose U, I'm getting basically, U1 transpose U1, U2 transpose U2 in the diagonals, and then the cross terms and the off diagonals. So the cross terms are all zero because these eigenvectors are orthogonal to each other. So U transpose U is equal to the identity, right? So that's a so-called spectral decomposition, and I can just take A to be C to the power of half, and it's pretty easy to see that AA transpose is going to be equal to C, right? So that's one possibility, and let's see what is actually happening then. So if I look at A times Z, where Z is your Gaussian 0, 1 IID random variables, what do I get? I get U lambda half U transpose Z. That's what I get. And that has the right covariance. I know that already. But the other thing to note is what U transpose Z is doing is transforming these Gaussian 0, 1s to a different coordinate frame. And it turns out that these, let me call this Z tilde, it's very easy to check that they are also IID Gaussian. Basically, there's this circular symmetry such that this rotation by this projection onto these basis functions does not change the distribution. So I can really generate the right covariance just by doing U lambda to the half Z tilde. So what's that actually doing? Just I can basically do U, and I'm now going to call it Z again. I'll drop this tilde. This is sort of Gaussian 0i. What's that really doing? That's basically saying I have lambda j to the power of half zj multiplying the vector uj. So I can think of this correlated Gaussian random vector with covariance C, I'm not talking about the mean yet, the covariance C, as basically being these guys, which are just Gaussian 0 lambda j random variables along these axes, these axes that are special. These are the eigenvectors of the covariance matrix. So they're not pointing along the natural directions that we might have chosen to start with. They're special directions associated with the covariance matrix. But once I change my basis to that, I just have these independent Gaussian random variables along these different directions, and the strength along a given eigendirection is the eigenvector. So the variance is given by that eigenvalue I meant. All right, so that's sort of the geometric interpretation of that. And of course, in order to add a mean to it, you just add a mean to it, right? So basically, plus U lambda to the half Z is Gaussian MC. So this is the desired distribution I want. So that's how you generate a Gaussian random vector. That's one way you generate a Gaussian random vector. Another way is to choose A to be the Cholesky decomposition of C. I'm not going to talk about that in detail, but suffice it to say that Cholesky decomposition looks like you're basically looking at the first element of the random vector, normalizing it, then looking at the component of the second element that is independent of the first element, normalizing that. So it's like a Gram-Schmidt decomposition, except I'm thinking of the individual random variables as sort of vectors. So this is very vague, and I don't want to go too much into it, but I encourage you to look up Cholesky decomposition, because that's a very efficient way of doing it. So all I'll say here is the Cholesky decomposition of a covariance matrix will look like C equals A transpose, where A is a lower triangular matrix. But so one way or the other, either by using spectral factorization or Cholesky decomposition, you factor the C and then you simulate it using that factorization.